equations. So before we go into the process of solving linear equations, we have to figure out, well, what is a linear equation? We've looked at equations so far in the previous section when we were solving ratio and proportions. Now we just have this extra term on there, this idea of linear. In math, linear really comes down to the root word line. And specifically, lines are created when we're solving equations that have x raised to the first power. So anytime that we have an equation that has x to the first power, we call it a linear equation. We have a whole different set of rules for solving those as we do for solving equations with x to the second power or third power and so on. So everything that we talk about in this section is all about solving equations that have x, or if there is an exponent up there, we just write a 1. Some important things about solving linear equations is first the nature of the solutions. So linear equations can have either one solution, x equals 3 or x equals 5 or something. A linear equation could have no solutions, or an x to the first power linear equation could have infinitely many solutions, meaning every real number that we can come up with would be a solution. So every number can be a solution, no number can be a solution, or one number can be a solution. What this means is that we can't have a finite number of solutions greater than 1. So in other words, if we solve equation for x to the first power and we get x equals 3, we know already that if there are not infinitely many solutions, there are no other values that will satisfy that equation. So solving x to the first power can't yield like two answers, like x equals 3 and x equals 17 or something like that. It can only be either 1, none, or infinitely many. The no solutions and infinitely many solutions, we're going to get to that later. Right now, let's just talk about solving equations that have one solution. Before we go into that, I want to talk to you about the 2 rules of algebra. When we're solving equations, there are 2 rules that we commonly use in order to make sure that we're playing by the rules of math. The first one is the idea of balance. I mentioned this in the last video, that an equation kind of has a scale-like to it. An equal sign is like where that scale is balanced out. So if I want to do something to one side of an equation, then I need to balance that out by doing the same thing to the other side of the equation. This keeps that equation in balance and it doesn't throw off the problem and create something that we didn't have in the beginning. So anytime that we want to do something, whether it's add, subtract, multiply, divide, in later math you may have to take the square root or something, all of those operations must be happening equally on both sides so that we keep the problem in balance, that we don't mess up the structure of it, what it was when it was given to us. The other rule of algebra is the idea of inverse operations to move. The goal of solving an equation really is to trim pieces away from the unknown value, trimming pieces away from x, until we just get x completely by itself. And so in order to move those pieces or to trim them away, we use the opposite operation of what's happening on that side. So if we have a plus 2 and we want to move that plus 2 out of the way, then we would subtract 2 from both sides. If we had a multiplication, maybe 1/2 times x, we'd want to move that 1/2 out of there by doing the opposite of multiplication, which is division. So imagine I have a problem like 2x plus 3 is equal to 13. Now we see a problem like this, you may be able to run through in your head and say, oh, okay, I can figure out just by plugging in numbers. 1, 2, 3, 4, 5, 6, 7, 8, and so on, until I find out what does that number have to be in order for these two sides to balance out. And technically that's not wrong. If you were able to look at this problem and say, oh, okay, if this whole piece right here were 10, then these two sides would be equal. And because I have a 2 right here and I'm multiplying, then x would have to be 5. 2 times 5 is 10, plus 3 is 13. Yeah, I'm done. Good job. The only problem with that is that not every problem in math comes out to be a nice, neat answer like 5. And so that's why it's really important to know what steps to take or the rules that you have to follow in order to get that x by itself. If this was some obscure problem and the answer ended up being, I don't know, 7 2/3 or something like that, it would be much more difficult for us to be able to just plug random numbers in until we get it. So just keep that in mind. The other thing I'll mention is that when we look at operations that we need to do, one of the big questions that comes up in algebra is, what do I do first? Well, remember when we were simplifying expressions using the order of operations, we had our good old friend PEMDAS. This is how we simplify numerical expressions. However, when we want to solve an equation, what we're doing is we're whittling those pieces away from x. And so really what we're doing is the order of operations in reverse. SADMIP. Keeping in mind that multiplication and division are on the same level, as well as addition and subtraction on the same level. And so really when we're solving equations, we're looking at what pieces are working with x. What are you doing to x? Well, we have a 3 here that's being added. We have a 2 here that's being multiplied. We don't have any parentheses. We don't really have any exponents. And so that's what tells us how we can start moving pieces away. According to this, we should be taking care of the addition and subtraction on this left side first. We have a plus 3 on this side. And so I'm also going to put this little line right here. You don't have to do this, but I do it in the beginning of algebraic equations just to show people, okay, this is where our scale is balanced. So this is our left-hand side, this is our right-hand side. And we want to get rid of our plus 3, so we're going to subtract 3 from both sides. Remember, if I do it on this side, I have to balance it out by doing it on the other side. The goal of subtracting 3 is to get rid of this number over here on the left. A plus 3 minus 3 is really just a 0, and so all I have left on the left-hand side is 2 times x. On the other side, I combine these like terms. 13 minus 3 gives us 10. Now we're on to the multiplication and division. We have a multiplication of 2, so to undo that, I want to divide by 2. Oftentimes you'll see most math teachers will write it as kind of a fraction form with a line underneath it. That's fine. If you want to do it like left to right and maybe write it like this, they mean the same thing. So it really doesn't matter. In this case, though, when we divide 2 divided by 2, we really get 1. It's not 0 that's over here. We're trying to get a single x by itself. Even though we don't write that there, there's technically like a 1 attached to it. We get our single x all by itself, or 1x, and on the other side, 10 divided by 2 is in fact 5. The cool thing about algebra, particularly solving equations, is that we can always check our answers to make sure if we're right by taking this number and plugging it back into the original problem and making sure that the two sides are equal. For this section, I will never make you do that, but I definitely recommend doing it on an exam or something if you have extra time, just to be 100% sure that you did it right. We'll look at another example. I'd like to look at one that has some fraction in it, because fractions are just scary looking. So here we have one that has 1/4, oh, I can't even highlight it, forget it. I give up. 1/4 x plus 13 is equal to 8. So it looks really similar to our previous problem. We have our scale balanced out over here. We have our x on the left-hand side. We have an addition that we're going to have to get rid of first, and then we have a multiplication out in front of x that we're going to have to get rid of by division. So our first thing we'll do is we'll subtract 13 from both sides. When I do that, I get 1/4 x is equal to -5. Be careful here, you have a positive 8 and a -13, so your minus or your negative value is got more power than our positive value. It's not just 5, it's -5 here. And then just as we did in the last one, we want to get rid of the coefficient in front of x, and we do that by dividing. So what we're going to do here is we're going to divide by 1/4. We have our calculator for that, and remember that dividing by fractions is the same as multiplying by its reciprocal. In this case, our 1/4 cancel out and we're just left with x. And on the other side, negative 5 divided by 1/4 is the same thing as saying negative 5 times 4 over 1, which is just negative 20. We'll do one more example of these. Suppose I have negative 5x plus 1 is equal to x plus 13. So this problem is real similar. The main difference in this problem from the previous problem is now we have, first of all, have 4 terms. 2 of those terms are alike. We have these 2 terms that have x in them, and then we have these other 2 terms that don't have x, the constant values. For these kinds of problems, I have just my own preference, which is to get x's on the left, constants on the right. So terms that don't have x are all going to be grouped together on the right-hand side. Terms that do have x are going to be grouped together on the left. That means that this x right here has got to move. It's in the wrong spot. It needs to be on the left-hand side. So to move that, I'm going to subtract x from both sides. This x hanging out right here is just a positive 1x. I need to move its entire term, so I don't want to divide. I'm not trying to get rid of the number in front of x. I need to move this entire piece. This is why I'm going to subtract this x. And again, if I want to do that, I need to balance it out by subtracting it on the other side. Notice that I write it directly below the other term with x. It's these 2 values that are being combined. When I do that, I get negative 6x on the left-hand side. I still have plus 1 equals. On the other side, my x moved, so I don't have it there. All I have on the right-hand side right now is 13. Now it looks a lot more familiar. We know we need to move this 1 out of the way. To do that, we subtract 1 from both sides. I get negative 6x is equal to a positive 12. And then to get x completely by itself, I divide both sides by negative 6. And this gives me x is equal to negative 2. So that takes care of solving linear equations with x to the first power that have one solution. I want to talk to you a little bit about what happens in the other 2 cases. Here's an equation, all x to the first power. Our goal in this one is going to be as well, solve for x. So it looks familiar. It looks like the previous problem, except there's even more terms going on here. The process, though, isn't any different. We want to identify which terms have x on them. We're going to make sure that all of those are on the left-hand side, and we're going to combine those. Before we even move pieces around, notice that we have a 7x here and a minus x here. So we can combine those right away. 7x minus a single x is going to give us 6 of them. So at this point, I have 6x plus 3 is equal to 6x plus 10. When you see equations that have the same amount of x's on both sides, bad things are happening. You're either dealing with no solution or infinitely many solutions. What we want to do first to determine whether we have no solution or infinitely many solutions is to get rid of these x's. I'm going to imagine I wanted to move this 6x to the other side, which is normally what we do when we solve equations. Get all of our x's to the left and our numbers to the right. To do that, I would have to subtract 6x from both sides. In the process of doing that, though, I get rid of the x's that are on the right-hand side and accidentally get rid of the x's on the left-hand side as well. All of my x's canceled out. To determine whether we have no solution or infinitely many solutions comes down to what we have left over after we get rid of those x's. In this case, we have something like 3 equals 10. Certainly we know 3 does not equal 10, and that statement that's left over is false. When we have a statement left over that doesn't make sense, like 3 equals 10, then that tells us that the original problem had no solutions. If we would have done this exact same thing and got something that was true at the end, then we would say it has infinitely many solutions. I'll give you an example of one of those. Let's try this one. Before we solve for x, we want to use our distributive property, send our number into both parts. When we distribute, we get 4x minus 8. Oops, sorry, these are supposed to be minuses. 4x minus 8 plus x is equal to 5x minus 5 minus 3. Then we can combine like terms. On the left-hand side, we have a 4x plus x, which is going to give us 5 of them. On the right-hand side, we can combine our minus 5 and our minus 3, and we get a negative 8. At this step here, we'd want to get rid of our 5x's. So we subtract 5x from both sides, and they both go away. The difference is, this time, we're left with a statement that does make sense. Negative 8 is equal to negative 8. The statement is true. Because we got a true statement at the end with no x's left over, then we know that this equation has infinitely many solutions. It means we could have plugged in whatever number we want and it would have made this equation true. That's it for solving linear equations. There's a practice quiz available for you to look at some word problems as well. And good luck in your work.